Yes, in this particular tutorial, we are going to discuss about sequences, and we're going to be interested in the whole that you need about the sequences. And you make sure that you have to understand that first we start with the definition of sequences. And sequences is defined by a sequence is the collection of terms which are arranged in specific order. So we can have collection of terms. Terms are just what can be numbers and or letters which are arranged in specific order. So you can have different orders of terms arranged together. For example, the terms of a sequence can be expressed as U1, U2, U3, U4, and UN. In other words, we can have as more terms as possible, which can be expressed as U1, U2, and UN, which N can be any last term. Second to that, you know that U1 represents the first term. Also, U2 is the second term. U3 is the third term. And then U4 should be the fourth term, and of also the nth term, which is the UN. And again, if you look at the example here, if I have a sequence of 2, 4, 6, 8, 2, 4, 6, 8, and 10, then 2 become the first term, 4 become the second term, 6 become the third term, and then 8 the fourth, 10 the fifth, and then blah blah. So I've explained that U1 is 2, U2 is that, and the U3 is 6, and etc. So let us start by the first sequence, that is arithmetic sequence. Now, and I've termed it as A. We'll be dealing with arithmetic sequence here. Then after that, I'll come to sequences with quadratic and cubic. Then after this, I think I'll wrap this so I can discuss about sequence of exponential. So the first thing you need to know is the sequence of arithmetic is a sequence whereby we do have a common term here. So if I can use this, a sequence of arithmetic is where we have a common term, and the common term is always given as D, or a common difference. That is just but how much is the successive term far apart. If you go ahead, like for example, I do have 3 here. I have 6, 9, 12, and 15. So if you look at their difference, you will get to understand that the first term is 3 and its successive term is 6. So you can see 6 here, and then blah blah. So if you get the differences between the two, you know that before we get the successive term of 3, we have to add 3 to get 6, and again we need to add 3 to get 3 to 6 to get 9, then 3 to 9 to get 12, then 3 to 12 to get 15. That is what we mean by the common difference. That's what we mean by the common difference. If you go ahead and you check on this, that is 7, 2, 3, -3, -8, -13. You'll also agree with me that there is a particular pattern with a common difference still as -5, because from 7 to 2 we have -5, which has been subtracted from 7. I also have negative 5 subtracted from 2, negative 5 subtracted from negative 3, and blah blah to get a common difference of a negative of 5. So what I'm trying to say here is, for arithmetic sequence, we do have a common term. We do have and there has to be a common term. There must be a common term. Good. Under arithmetic sequence, still, we are still talking about other formulae for the terms of an arithmetic sequence. Other formulas for the term of arithmetic sequence. For example, the first concern is a term-to-term rule. Now, under this formula, we only have two ways at which we can define or describe or any other sequence. For example, you can see here we do have a term-to-term rule. So sometimes in exam you can be asked to give a term-to-term rule of a specific sequence, and this is what you are required of. For example, in this sequence here, we do have 7, 12, 17, 22, and 27. If you look at the successive differences, for 7 to get 12, we have a positive of 5, and for 12 to get 17, I have a positive of 5 still. So the common difference here is positive 5. Now, the term-to-term rule for this particular sequence is positive 5. In other words, I'm adding 5 to the previous value to get the next value. And that one can be, now if for example I would want to get the second term, that is 12, I'll need the first term, then I'll add 5. So you can check, I'll need the first term, which is u1, and then I'll add 5 to u1 to get 12, which is the second term. And also here, for me to get the third term, I'll need, for example here, I need u3, which is the third term. So u3 will be equals to u2. u2 is 12 plus 5 for me to get 17. u2 plus 5 to get 17. Now, in general, what we are talking about here is, in general, the term-to-term rule. The term-to-term rule of this particular sequence is just but un plus 1. un plus 1 is equals to un plus 5, where un is the nth term and un plus 1 is the term after nth term. Let's see again more of the examples of the same. Given the same example, let's say that we need to get you need to get the value of before, the value after 17, which is 22. So I'll have un plus 1 is equals to 17 plus 5, which is 22. un plus 17 is equals to 17 plus 5, which is 22. And it is also important to note that in a scenario whereby you are asked to list the successive sequences, then you must be given the first value. You must be given the first value. You will see such cases in the examples, and you also see such cases in some of the questions that you will be having. And now you just need to know that if you are asked about that, they must give you the first value. At least you can apply now this formula to give a general sequence in terms of values. The second method, or the second formula to find arithmetic sequence, is the formula for nth term of a sequence. The formula for nth term of a sequence. Now, when we're talking about the formula for nth term of a sequence, what we are saying here is the type of rule links each term to its position. This type of rule will be linking the position of the term and the term itself. For example, now say that I have a term of 7, 12, 17, 22, and 27, the same example here. If I do have that particular system, and now 7 in this sequence takes position 1. So then its position is 1, and then 12 takes the position of 12 of the second value, then 17 is the third, 22 is the fourth, and 27 uh, is the fifth, up to the nth term. Now, if I don't have such type of sequence, and I want to use this formula of the nth term of the sequence, what I do here is that you should be able to see that from the example above, each term can be calculated by multiplying its position number by adding by 5 and then adding 2. So if I would want to get the position or the nth term here, only for example 7, okay, 7 is in position 1, so 7 here is in position 1. I'll need to multiply 7. I mean, for me to get 7, okay, for me to get 7, I'll have to multiply the position number by 5, then I add 2. So the position number here is 1, so 1 times 5, then add 2. 1 times 5 is 5 plus 2, I get 7. Now that is about the formula of the nth term of a sequence. And algebraically, we can represent this algebraically by un is equals to 5 times the position, then add 5. For example, again, if I would want to get the fourth position value of this sequence, then I will do this. Let me wrap this. Then what I will do here is I will take the position which is 4, I multiply by 5, then I add 2, so that is 20 plus 2, I get 22. So that is another formula of getting the nth term of this sequence. You have to note again that the rule for the nth term can be easily deduced by looking at the common difference. The rule of the nth term here can be easily deduced by looking at the common difference. For example, if you look at this example, that example above here, that we have term of the first, which is 1, 5, 9, 1, 5, 9, 13, and 17. 1, 5, 9, 13, and 17. So the position of 1 is 1, the position of 5 is 2, the position of 9 is 3, position of 13 is 4, position of 17 is 5. If I want to get the nth rule here, I simply look at the common difference. So if I look at the common difference here, I see it is positive 4, so I just have 4n And then, so if I have 4n, but now I need to get 1, what is done here? You subtract 3. So 4 times 1 minus 3, I get 1. The same to any other value. If I would want to get this 13, I just take 4 times 4 minus 3, which is still 13. All this will still apply to this second example and this third example. And let's look at this third example because it has a difference of a negative. Let's look at this third example because its difference is a negative. Now, if I want to get the nth term of this sequence, so that if I'm asked to get maybe get the 20th term, get the 50th term of this particular sequence, get the any other term that is given, but you have to apply the law. So if I have this, let's say I need to get this, how many are this? 1, 2, 3, 4, 5. Let me say that I need to get maybe the 7th term of this sequence. But remember, I only have up to 5th. I only have up to 5th. That's the first, second, third, fourth, and 5th. What if I need 7th? So what I do is I use the formula because now I have used the sequence that I have, and I have now come up with the nth term, which for me to get 12, I just multiply 12 by 1, then that is sorry, for me to get 12, I have to multiply negative 3 by 1, then add 15. So negative 3 by 1, which is the first value, that's negative 3. Then if I add 15, I'll get 12. So this is the rule which has been used to form this sequence. So if I need to get the 7th sequence, or rather the 7th value, I'll need to have negative 3 times the position, which is 7, plus 15. So negative 3 times 7 is negative 21. 21 plus 15, that is 6. That is 6, which is negative. So I'm getting negative 6. And that is why we are saying this is very helpful when you are asked in a question to get the any term of a sequence. Now, let's see about conclusion. We are saying in our conclusion that all that we have been discussing about in arithmetic sequence, that the term to term rule has a common difference. That is the first point to note, that the term to term rule has a common difference. And the rule for the nth is linear, then it has to take the form of an plus b. Just like equation of a line. Just like equation of a line, yeah? Whereby we are told that y equals to mx plus c. You see, the highest power of x is just 1, just like the way highest power of n here is 1. Now, let's do sequences with quadratic and cubic rules. Sequences with quadratic and cubic rule. Now, under these sequences of quadratic and cubic rule, what you need to understand here is we are going to still try and find the common difference of each, but the only difference here is we have to use the second difference and the third difference to at least get the second, to at least get the common difference. So it is different in a way of arithmetic here, because we only had to do a first difference to get a common. But for quadratic and cubic, you'll realize that we need to go to the second thing, because we are trying to subtract, but we cannot still get the common difference. Now, what happens? For example, you can be given a sequence like this and you are told to reduce the nth term of the sequence. So a sequence of A, 4, 7, 10, 13, and 16. What do you need to do for you to at least deduce the nth term of this sequence? What you have to do is, first you need to form a table. Step 1, produce a term of the table. Produce a table. So here should be produce a table of the term. So the table should be having term and the positions in the sequence given. So position and term. In this sequence, I have 4, 7, 10, 13, and 16. I have 4, 7, 10, 13, and 16. And 4 is taking the first term, 7 is taking the second term, and 10 is taking the third term, and 13 is taking the fourth term. Lastly, 16 is taking the fifth term. After you've produced that, the second step is to extend the table to have the difference. Extend the table to have the difference. Now, if I extend the table to have the difference, I'll have 3, 3, 3, 3. So in this, the difference between 4 for me to get 7, I add 3. For the difference for me to get 10 from 7, I add 3. And again, I add 3 and I add 3. That's the first difference. And you should be able to note that in this particular example, it's still a linear. It still brings us back here. Because in the first difference, I'm able to get the common. But now, as the rule of the first difference is constant, now the rule of the nth term is still linear and is still taking the form I discussed about here. Now, I wanted to pay attention now here, because this is now the most challenging thing, and it's going to lead us to cubic and quadratic. If you don't understand it now, it's going to be a problem. Let's see. I would want to substitute in this value of n into the rule, and then each term can be represented in A and B. In other words, I want to use this rule, and I would want to represent each and every term, that instead of writing 4, I just say 4 is in the first position. So I come here and say, because I have the law of n is equals to a n plus b, and I want to get 4. 4 is in the first position, so n is 1. So I have a plus b. So a plus b will represent for me 4. And if I want to get 7, I just know that 7 is in the second position. So I'll have, so here should be n of 1, n of 2, n of 2, I will have 2a plus b. Now this is the way you can substitute it to represent your answers in terms of a and b. So I've come here and done the same. So I can have a plus b for the first position. I can have 2a plus b for the second position, and then I have 3a plus b for the third position, then I have 4a plus b for the fourth position, then I have 5a plus b for the fifth position, as you can see here. Then now, my common difference a is a constant. My common difference here is 3, which is a constant. And now, because it is 3, I'll represent it by a common term a. Okay? By a common term a, and a. Now, let me use this to at least come up with the rule for the nth term. I want to come up with a rule for the nth term. So if I use this for my nth term rule, I say that if I know that a is 3, my first term, my difference is a is 3. So if a is 3, and now for the first term, which was 4 here, I know it is a plus b. So what I do is I have a plus b, which is equals to 4. Then now I can find my b as 1. Because now I know my b as 1, I know my a as 3, I can now have the rule and say that this sequence here was formed under this law of 3n plus 1. This sequence here was formed under the law of 3n plus 1. Now you will realize that this method for linear, for finding the nth term, is a bit of complex compared to this first and the second. But now it is more of significance, and it helps us most when finding the cubic sequence and the cubic sequence. How will it help us? Let's see. If I have another example of a sequence that is 0, 3, 18, 13, and 32, I'll first form the table the way we did in the first scenario here. And then if you form the table that 0 is in the first position, 7 is in the second position, as you can see that 18 is in the third position, so we have 3 there, 13 is in the fourth position, so we have 4, 52 is in the fifth position. If you try to get the difference between 0 and 7, which is 7, and also try to get the difference between 7 and 18, which is 11, then the difference between blah blah, and now we have 7, 11, 13, and 19. That is if you try to get both of their differences. You'll realize that these differences are not common. Take a minute and think about it. These differences are not common as what we are doing in the first place here. So if they are not common, what we are doing here is we are going to the second difference and at least try to find that at what level are they appearing to be common. Good. So I go to the second difference. Then now I drop another row of second difference. So the difference between 7 and 11 is 4. The difference between 11 and 15 is 4. The difference between 15 and 19 is again 4. Now at least we have a common difference, but at the second difference. Now this is what we call quadratic rule. Now the rule of the second difference is constant, so the rule of the nth term is quadratic, which takes the form of un is equals to an squared plus bn plus c. Again, this is the same as the cubic expression, that is ax squared plus bx plus c. Now, the whole idea here is to come up with the nth term of this sequence, so that whenever I'm asked to get about any other position of a value, I can use the nth term rule to find any number, maybe the 100th term, the second term, the 10th term, any other position that I'm asked, I will then be able to calculate and find. So if I use this rule, my interest is to get A, B, and C, because n is just but the number of position. So substituting the values of n into the rule, in other words, if these ones have n, then I have the positions here. Now I want to substitute these positions in here. So can I rewrite? Then I can as well rewrite the first term as, in terms of A, B, and C. So substituting the values of n into the rule, each term can be expressed in terms of A, B, and C. Each term can be expressed in terms of A, B, and C. And if you look at each term here, for the first one, that is 0. If I express 0, let me just use this part here. The rule is un equals to an squared plus bn plus c. Let's say we want to find u1. Let's say that we would want to find u1. So if I replace n by 1, I'll have a of 1 squared plus b of 1 plus c. So 1 squared is 1, 1 times a is still a, b times 1 is still b, then plus c. What if I want to get the second term? So if I replace with the 2, I have a into 2 squared plus b into 2 plus c. So 2 squared is 4, so I'll have 4a plus 2b plus c. Let me try and do the third term in terms of a, b, and c. So I'll have u3 is equals to a into 3 squared plus b into 3 plus c. So 3 squared is 9, so 9a plus 3b plus c. Good. Well, if you look at what I've done in the term, it's exactly what I've explained here. And now we have a plus b plus c. Then we have now 4a plus 2b plus c, which is 4a plus 2b plus c. Then we have 9a plus 3b plus c, so 9a plus 3b plus c. And again now the fourth term and the fifth term. If I want to do the fourth term, I still have a into 4 squared plus b into 4 plus c. So 4 squared is 16. 16 times a is 16a plus 4b plus c, and blah blah up to the fifth term of this particular sequence. Now if I do them like that, and then I now have the first term represented as this up to the fifth term, then I go to the first difference. What first difference gives me is, let me just wrap this, then I can do the first difference. What first difference is giving me is I'm trying to subtract the successive terms. So if for the first one, just the way I subtracted 7 and 0 to get 7, so I'll subtract 4a plus 2b plus c minus a plus b plus c. So this is the second term, this is the first term. If I subtract them first, I will do by expanding the bracket. So what I'll do is I'll have to repeat the first one, then I open the bracket by multiplying what's outside. So I have negative a, negative b, negative c. Then I can now collect the like terms, that is 4a minus a plus 2b minus b plus c minus c. So I have collected the like terms now, and then I now have 4a minus a plus 2b minus b plus c minus c. And if I simplify this further, I'll remain with 3a plus b. So 3a plus b is my difference between the second and the first. And even if I would want to do the third and the second, which you can do, and you'll be able to realize that the difference between the third and the second is 5a plus b. You should be also able to realize that the difference between the fourth and the third is 7a plus b, and then the difference between the fifth and the fourth is 9a plus b. Good. Because I did not find similar term here, again I'm not seeing a similarity here, okay? Because I'm not seeing a similarity on the first difference, I'll go to the second difference and again try to subtract this from this, just the way I subtracted 11 and from 7 from 11. So I'll subtract. If I subtract 5a plus b as the second term, then I minus it with 3a plus b. What I'll remain with is 2a. b will be 0 because b minus b is 0. And then maybe I just do it here. What I'm saying is if I subtract the 5a plus b minus 3a plus b, what for me to do this, I'll again need to expand the bracket by opening it with the sign outside. So negative times 3a, I'll get 3a. Negative times positive b, I get minus b. So if I collect the like terms, I'll have 5a minus 3a, then plus b minus b. So 5a minus 3a, I get 2a, then b disappears, so b becomes 0. So then the difference I'll be getting is a constant of 2, 2, 2, 2, a, 2a, 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 2a. Now, again, listen to me. If you reach here, it's not the end, okay? You'll still now have to at least try find the values of a, values of b, values of c, because that is the main goal of our sequence. So I'll have this up. Now, for me to get the values, I know that 2a is 4. I know that 2a is 4, so I equate them. 2a is equals to 4. What for me to get them, just comparing the tables and the values. So I compare the second table and the first table. So I have 2a is equals to 4. And then I also have the first term, which was 3a plus b equals to 7. So 3a plus b equals 7. So if 2a is equals to 4, then a itself is, I divide both sides by 2 to get 2. Then 3a plus b is equals to 7. I already know a is 2, so I substitute it here. So I have 3a times 2. Like now I'm substituting a with 2. So 2 times 3 is 6 plus b is equals to 7. Then b become 1. Now I already have b and already have a. I'm now remaining with c. And I know very well that the first term here was 0. Okay, so I equate them. 0 here, 0 here. So a plus b plus c is equals to 0. I already have a and already have b. What is c? So a, which is 2, I substitute it here. Then b, which is 1, I substitute it here, plus c equals to 0. Then I remain with c, which is if 2 plus 1 is 3, so the whole of this gives me 3 here. If I move this 3 into the other side of the equation, it becomes negative 3. So c is negative 3. So I have both terms. What I only remain with is to substitute them into the formula. So according to the formula of quadratic, where a n squared plus b n plus c, so 2 is a, then b is 1, so it's still n, then c is this. So this formula, which c is negative 3, so this formula, you can use it to get even the 11th value of this sequence. You can still use it to even get the 100th value of this sequence. You can even still use it to get any other value. Now you can use the formula and now it becomes very easy. That's why it is very important to know what you are dealing with and how you are dealing with them, and even how to find the formula of each term. Now, I'm remaining with the last one, which is the exponential. So I'm gonna rub all this so I can do the exponential one. I'm gonna rub this so I can do. Now, before we look at the exponential, let us finish with the cubic sequence. And if you look at here, we have an example C, and we want to deduce the rule for the nth term for the sequence of -6, -8, -6 again, then 6 and 34. Now, what I have done here is we want to look at what scenario can we apply the cubic sequence. Remember, we have looked at the normal arithmetic sequence with the first difference. We have looked at the quadratic sequence with the cubic difference, and now we are looking at the quadratic sequence with the second difference, and now we are looking at the cubic sequence with the third difference. Now, the same way we did for The other one, this is position 1, so negative 6 is in position 1. As you can see here, that negative 6 is in position 1, and negative 8 is in position 2, negative 6 again in position 3, then 6 in position 4, and then 34 in position 5. The first difference, if you do, you will get negative 2, and then that is negative 8 and 6, you get negative 2. Then the difference between negative 8 and negative 6 is positive 2. Then the difference between negative 6 and 6 is 12. Then the difference between 6 and 34 is 28. Having said that, the second, you'll realize that the first difference still is not giving us a constant difference. So we'll have to go to the second difference. And if you do the second difference again here, that the difference between negative 2 and 2 is 4, the difference between 2 and 12 is 10, the difference between 12 and 28 is 16. Still, we don't get the same difference. So we have to go to the third difference, and that's what brings to us the cubic arithmetic sequence. Now, if you do the difference between 4 and 10, you get 6. The difference between 10 and 16, you get 6 still. So now that the row of the third difference is constant, the row of third difference is constant, the row of third difference is constant. Down the nth term rule is therefore cubic. That's when we now get cubic, and we talk about cubic. And then now the nth term rule is cubic, and the cubic is given in the form of un equals to an cubed plus bn square plus cn, but now we are now adding another term, which is d, constant d. Again, this is the same as the cubic equations which we did before, or you are supposed to be doing. Now, by substituting the values of n into the rule, each terms can be expressed in terms of a, b, and c. Now, we just want to express these terms here in terms of the first term as a, b, and c, and d, then blah blah, up to the fifth term. Now, for us to do that, because we've known the formula as an cubed plus b squared plus cn plus d, we will use the formula and just substitute the positions of each term. Now, the position of each term here are: the first position give us negative 6. The second positions give us negative 8. So the first position here, if I substitute n by 1, then I cube 1, I still get 1. So a times 1 is a. So that's why I have a here. And then b times 1 squared is still b. That's why I have b here. And then c times 1 is still c. Then d do not have n, so it still remains as constant. Now you'll agree with me that if you continue and even substitute for 4, and now you'll have 4 cubed, you'll get 64a, and then you'll have again 4 squared b, that is 16b, and then this is 4c. So what I did in the whole row here that way is I was able to get, for the first term, a plus b plus c plus d. Then for the second term, this is 8a plus 4b plus 2c plus d. Then for the third term, this is 27a plus 9b plus 3c plus d. Then for the fourth term here, this is 64a plus 16b plus 4c plus d. Then the last term, that is the fifth term, this is 125a plus 25b plus 5c plus 8d. You can as well substitute them on your side and find out if you are getting the same thing. Now let's come back and proceed. If I did the difference between the first and the second on the first difference, so if I subtract the second term, like that is 19a plus 5b minus c, if I subtract 7a plus 3b plus c, I am able to do it this way. So that is 9a. I'll repeat this, then I'll remove the bracket by multiplying whatever is inside by what is outside. So this negative 7a minus 3b minus c. So if I collect the like terms, which are 19a minus 7a plus 5b minus 3b plus c minus c. So 19a minus 7a will give me 12a. Then 5b minus 3b will give me 2b. Then this will give me c minus c will give me 0. So what I have is 12a plus 2b. That is what I have here. The same thing here. Now you do it that way. Again, subtract the successive terms, this from this, again this from this. You are supposed to be able to get the other two that way. Because the second difference is still, or that was still not constant, then I go to the third difference. And the third difference, as this was now, if I subtract this from this, I get, if I subtract 18a plus 2b from 12a plus 2b, I should be able to get 6a, and that's what I got. And the same if I subtract 21a plus 2b minus 18a plus 2b in bracket, I should be able to have that. A quick one on comparison. A quick one on comparison. Now, I'm comparing the two tables. Then if I compare the two tables, then I should be able to form the values of A, B, and C, D. Remember, I told you that the main goal here is to get the nth term. And all these processes we are using to get the nth term are different depending with the different sequence we have. So for you to get the nth term, you need to understand these different steps and systems that we are using to get the nth term formula. So I should be able to get this formula if I substitute any value. Let's say maybe you are asked to get, so 1, 2, 3, 4, 5. You are asked to get maybe 12th term here using the formula. You're supposed to get even the 1000th term. So by comparing that, I know that 6a is equals to 6 here. So I'm comparing this and this. So 6a is equals to 6. Therefore, 6a is equals to 6, then a is 1. If I compare the second one, that is 12a plus 2b. So because that I already have a, I'll now just compare 12a plus 2b. So 12a plus 2b is the first difference here. So they are the same. Just equate them. Just equate. So I'm able to substitute a with 1, then remain with b, then b, the value of b become 4, which is negative. Then again I proceed and find the value for c, and 7a plus 3b plus c was giving me a negative of 2. So I compare this negative 2 and 7a plus 3b plus c. If I simplify that and substitute the values of a here as 1 and b here as negative 4, I should be able to get the value of c as 3. Then lastly, if I substitute the first term, that is a plus b plus c plus d, is equal to the first term, which is negative 6, and my a was 1 and b negative 4, then c was 3. If I substitute them here, I'm able to get d as negative 6. Now that I have all values of a, b plus c plus d, all values of them, I do have them here. I just substitute back to the formulae of the nth term, and then doing that, I'm able to come up with this formula. Good. Last concept is exponential. Last concept is exponential. Now, understand this. All that we have been doing are related to arithmetic in a way that we are finding the common difference. As our second thing, that is the last thing, C, that is exponential sequence, we are not going to focus on D. Note that D is only applicable to arithmetic sequence for both cubic, quadratic, and linear. But here we are going to use common ratio to find the sequence that is used to write those particular sequences. So that is the difference I needed you to note down. Let's come here now. Exponential sequences, a sequence where there is a common ratio given as r, a sequence where there is a common ratio given as r between successive terms is called exponential or geometric sequence. So whenever you hear the term geometry, just know that they're still referring to an exponential system. So there are two things meaning one. So for example, we have a sequence of 2, 4, 8, 16, and 32. 2, 4, 8, 16, and 32. You will agree with me that for us to get 2, we multiply 2 by 2 to get 4. So that for us to get 8, we multiply 4 by 2 to get 8. For us to get 16, we multiply 8 by 2 to get 16. For us to get 13, we multiply 16 by 2 to get 32. Then the sequence is 2. Yeah. So this becomes our sequence, our ratio. Sorry, the ratio is uh, 2. Likewise, for us to get 9, I have to divide 27 in this second sequence. I have to divide 27 by 3 to get 9. I also have to divide 9 by 3 to get 3. I also have to divide 3 by 3 to get 1. And I also have to divide 1 by 1 to get still 1 over 3. So the ratio here is 1 over 3. Then we come to formulae. We come to formulae that we were talking about the other time. We are saying that formulae for describing exponential sequence, one, we still maintain the same formulae in arithmetic, but now the one which we are using in arithmetic. So the formula here is one, the term to term rule, that one we had discussed about in arithmetic, but now here, for example, if you look at 3, 6, 12, and blah blah, you should be able to know that the first term has been doubled to get the second term. The same as for you to get the third term, you have to double the second term. So that's the term to term rule. In general, the nth term here is a double of un, and you must also be given the first term. That one I said. And then in the second formula, for the nth term of an exponential system, we have the formula for the nth term of an exponential system. For example, if you are using the same sequence here, the second formula always link the position and the term. So we have the first position and the value of the term, and again we also have the second position and the value of the term. Again we also have a blah 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 up to the nth position and the value of the nth term. Like here, the 3 maintain the first term, 6 maintain the second term, and 8 maintain the fifth term until nth term. Now, if you see what is done to 3 to get 6 is 3 multiplied by 2, and then for us to get the third term, 2 times 2 times 2, 2 times 2, that is 2 square. Then for us to get the fourth term, that is 3 times 2 times 2 times 2, so 2 cube. So you get that. So then the nth term is 3 times 2 power n minus 1. The nth term is 3 times 2 power n minus 1. We are subtracting n and 1 because we have started with the second term here. Okay? So, which is n2. So n1 is the one which we are reducing here. Okay, now in general, you will agree with me that the formula for the nth term for this sequence, that is the geometric sequence or the exponential, is un is equals to a times r power n minus 1, where a is the first term and r is just the ratio. Now the last concept here is we are trying to look on how we can apply the geometric sequence or the exponential in real life. So applications of exponential sequences are: one, you can use compound interest. Remember that compound interest we're also using in simple interest thing calculations, where we are given the principal, we are given the time, and you are asked to calculate maybe how much time money has compounded in what period of time. And it's also used in most of the financial institutions where they are calculating the profit of interest of the principal money given to their clients. So if a client can buy the idea of that particular financial institution to invest with them, that is okay. Now here what we're doing is we're trying to tell you that we are also applying compound interest in terms of exponential. For example, if you invest $100 and in a bank, you deposit $100 in a bank, and you don't touch that money for the next 1 year, and then you realize that the money has increased to $110 as a result of interest payments. Now, for you to calculate the interest rate and the amount after 5 years, you come here and say that the interest rate is equals to the successive money divided by the principal, or rather the first value. So if I divide 110 by 100, I get 101. And then if for number B, if you ask me to calculate the compound after 5 years, then it means that what I'm going to do is I'll use this formula of compound, of the geometric sequence to calculate here. Okay, so if I use for the n equals to 5, then I raise the power to 5. And please take note that here we are raising the power to 5 just because there's a note, the number of year starts from 0, as just apply 5 directly in the terms of power, so we don't need to subtract 1. That is the difference. That when you are applying compound interest when calculating geometric sequence, okay, you don't subtract 1, because the number of years start from 0. So in other words, we have like 5 years. 6 years. And these 6 years, you less 1 to get 5. Then you calculate your value and you get 161.02 as the money that you will get in terms of the compound interest after 5 years. And then we also have the sequence in terms of the numbers arranged. You say that the 0th year you got this, the first year you get this, second year you get this, blah 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 blah, up to the last 5th year. If you go to the last bit of sequences, that is combination of sequences. We are trying to ask you in this topic again to understand that what we have learned up to now is very useful and applicable. However, if you realize that there is a way you are given a sequence and you can rewrite this sequence in a certain way that it can form the key sequences, like a sequence of squares, a sequence of cube, a triangular sequence, and other more sequences, then it is advised that you don't need to go the long way, but you can as well do this other way. Let's look at this way. When combination of sequences, suppose you are given this sequence here. An example is this one. You are given this sequence, and then you are asked that to form the nth term formula for this sequence. If you look at this sequence, you will agree with me that the second difference is common. Yeah? But I'm now telling you that you can do it this way and they follow the same procedure we have been using to find the nth term rule. However, if you realize that you can rewrite this sequence in a way of having 1, 4, 9, 16, and 25, just by subtracting 1 in each term to have 1, 4, 9, 16, and 25. It means that 1, 4, 9, 16, and 25 is a key sequence. It is a key sequence because it forms a square number. These are just some of the key sequences that I've had to note for you. You need to take question of them. Now, then it means that each term in 2, 5, 10, 7, 26 has 1 which is added to it. Okay? From this, for me to get this from this, then I add 1. Okay? Now, the new sequence that is a key, which is 4, 1, 4, 9, 16, and 25, is a sequence of square numbers. Therefore, the formula of the nth term in a square number is this, which I've written here again. So that is something you should be knowing by heart. Therefore, the formula of nth term for the sequence, which we had 2, 5, 10, 17, and 25, 26, is the formula of a square number plus 1. Okay. And then lastly, take note of the key sequences and know them by heart. That a sequence of numbers 1, 4, of square numbers, that is 1, 4, 9, 16, and 25, is un is equals to n squared. Then a system of cubic numbers, that is a cube of 1 is 1, a cube of 2 is 8, a cube of 3 is 27, cube of 4 is given as the nth term is n cube. Then a key sequence for the powers of 2, that is 2 power 1 is 2, 2 square is that 2, a power of 2 is given as un is equals to 2 power n. Then we have the triangle numbers. Triangle numbers. If you look at this system, we do have the difference here are 2, the difference here is 3, the difference here is 4, the difference here is 5. So it is triangular in the sense that it is successive. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So such sequences, they have a formula of un equals to half n into n plus 1. Now, these are all that you need for sequence, which is chapter 15. For more, we'll be doing, and you can always ask questions in regarding this or any other topic. Thank you.